nanohub.org.
So today we're going to move on to the next part of the class, which is going to cover, I would say, nearly 3 weeks now, or at least 2.5 weeks, and this on dynamic AFM methods. And the idea of dynamic AFM methods is basically, I think I showed this to you last time. If I can just get this video up and running a second. Basically, what happens in dynamic AFM is you take the cantilever and you shake it up and down harmonically, right? Apply some sort of a sinusoidal forcing, and as opposed to slowly moving it up and close to the sample. And you do it at resonance, so you excite it at resonance, and what you start seeing is it starts oscillating in a very characteristic shape at certain specific characteristic frequencies that are called the resonance frequencies of the cantilever. Okay? The reasons for moving to dynamic AFM from static AFM are actually there are many reasons. One of the key disadvantages of contact mode scanning is that you're always in contact with the sample, and so you're always applying lateral forces. And so if you have any weakly bonded, particles that you're trying to image, you're basically brushing them off. It's brooming. In fact, there have been some semiconductor cleaning techniques based on contact mode scanning. You just basically clean things off because you push them away, right? So the idea was one of the early ideas was, how do you scan while minimizing lateral forces? And one way is, let's do it intermittently. Let's not be contacting all the time. Let's just do intermittent. Okay? And so the idea came up, let's do dynamic AFM where the cantilever actually oscillates and, only once every cycle for a short time actually interacts with the sample. So you reduce the lateral forces. Okay? That's one. The second thing is, from the early days of AFM, there was a lot of interest in measuring F versus D. This is a very fundamental measurement you want to make, as we've discussed before. And there's a problem in trying to do F versus D with using static approach retraction curves, right? So what's the disadvantage? The main disadvantage, if you remember, is you cannot recover the entire FD curve. There's a big gap that you have. Do you remember that? Because you snap it and you pull away, there's a part of D range that is not accessible. I hope you remember that because it's the essence of doing FZ to FD conversions, right? So you don't capture, so you're not able to get part of the interaction force. In an experiment, you might actually see a continuous curve F versus D, but a lot of that data, you can tell, is actually transient as the cantilever is snapping from one place to the other. It's not real, equilibrium positions, okay? So the idea was, okay, if we cannot use static FZ curves to back out the FD completely, why don't we keep the cantilever far away and make the tip oscillate and go all the way through the interaction potential, tap on a sample and come back, right? If you do that, you're not snapping in, but you're oscillating, and the tip is basically traversing the entire range of tip-sample interaction. So why don't we do that instead? So we avoid the snapping in kind of instability. Okay? So both reasons, for reasons of reducing lateral forces while scanning, and for being able to do force spectroscopy without having the cantilever snap in, right? These are the two reasons to try and move towards dynamic AFM. Now, there are many different types of dynamic AFM. I've listed two. Broadly speaking, they're categorized by amplitude modulated or frequency modulated, right? This is terminology that you'll see in the reader in the article by Garcia and Perez, for example. And what this refers to is not an amplitude modulated signal. What it refers to is that when you scan the sample, you make sure that the amplitude is kept constant. Okay, that's what amplitude modulation means. The frequency modulated signal, or the frequency modulated scheme, would imply that as you scan the sample, you keep frequency constant, which is true, except in frequency modulation, it turns out you not only keep frequency constant, but you also keep amplitude constant, and you also keep phase constant. So technically, the FM, AFM ought to be frequency, amplitude, and phase, FAP, modulated AFM. If you want to stick to terminology about what is the quantity that's held constant, in AM, it's only the amplitude. You move the base of the cantilever up and down to keep the amplitude constant as you scan over a sample. In frequency modulated, we'll discuss this later, you keep three things constant: phase, amplitude, and frequency shift. Okay, so the amplitude modulated AFM is what was originally patented as tapping mode by Vico, which is now owned by Brooker Instruments. And for the longest time, when you write tapping mode, you're supposed to write trademark on top of it. Right, so. Okay, so to give you a brief idea, again, we covered this some time ago, but what's going to happen is, and we'll do this in more detail when we go to eigenmodes, there's a difference in the shape the cantilever takes when you just apply a point force at the end of it, and when you actually drive it at resonance. There's a difference in the shape. In fact, you know that in the case of when you apply simple point load, you know that the deflection curve is given by this cubic equation given below, x over L cubed plus x over L squared. There's an extra x cube. There's an extra x cubed that shouldn't be in this equation, right? But it's basically the first term is x cubed, the second term is x squared. That's the curve, the deflection curve of the cantilever when you apply a point force statically, very gently apply a force, okay? On the other hand, if you take it and you apply a harmonically exciting harmonic force that drives this cantilever at its resonance, the shape that the cantilever takes is a shape of what's called the eigenmode of the cantilever, which we'll talk about. And the first eigenmode of the cantilever has an equation that's shown there. And you can see it involves cosines, cosine hyperbolics, sines, and sine hyperbolics. And therefore, that shape is not really like the simple cubic equation shown here, okay? But on the face of it, it might, if you just looked at it with your eye, you might think that they look similar, but in reality, the equation is different. Now, what does that mean? Let's go down to the equation below. One consequence of the simple cubic relationship deflection curve is that the theta, which is the slope at the end of the cantilever, which is what you measure in an AFM using the photodiode, right? You're measuring the bending angle at the end of the cantilever. That's theta. And delta is the up and down deflection of the tip. Theta over delta, in the case of a static bending, is 2L over 3, well, L is the length of the cantilever. So we've done this before in class, right? So what it means is that by measuring theta, you're effectively measuring delta, and the proportionality constant is 2L over 3, all right, when you do static AFM. On the other hand, for dynamic AFM, the ratio of theta to delta is no longer simply 2L over 3, it's something else, okay? So right away, it tells you that when you do your deflection calibration, i.e., you convert volts to nanometers using a static curve, that volts to nanometer conversion will not be exact for when you do dynamic AFM. There's going to be a factor. We're going to talk about all this later. I'm just laying out some of the issues that are going to come ahead. Okay? Nonetheless, so the fact that the cantilever is actually a continuous beam with a tip adds a lot of complexities. However, to begin with, what we'll do is we're going to start with what's called the point mass model. The point mass model says that, look, I don't want to worry about these eigenmodes. As far as I'm concerned, the cantilever is basically a spring, and whose spring stiffness is the same as that of a cantilever where you apply static force at the end, which is 3EI over L cubed, okay? So it's the static bending stiffness of the cantilever. And so I'm going to replace it by a spring, and the tip I'm going to replace by a mass, and just put it there, okay? which is again sort of interesting because you neglect the mass of the cantilever itself. You just say it's a tip, that's the mass, and the cantilever simply acts as a spring. Now, you obviously realize that you can't just impose these things. You know, at some point you have to model it and make sure it's right. But nonetheless, this is what's done in the point mass model. So the point mass model replaces this with a spring and a tip. Spring constant is the static bending stiffness of the cantilever when you apply a force at the end of it. So let's look at this model then. We've got a spring whose spring constant is K. This is the spring is the stiffness, static stiffness of the cantilever. Now we also have to account for some dissipation, right? So what's going to happen is, as you take this tip and you pull on it, it's going to oscillate. I mean, if you let it go, it's going to oscillate, but it's going to damp out, right? So we have to allow something that allows. We have to include something in the model that allows the damping process. So one simple way in mechanics is to introduce this dashpot, a viscous dashpot, basically, which is an element that basically dissipates energy, and it applies a force proportional to the velocity of the tip relative to the base. Okay, so it's a viscous resistance basically that applies a force opposite to the direction of motion, but linearly proportional to the force to the velocity of the tip relative to the base. So if you do a simple free body diagram of this system, oh, and by the way, we're going to begin with something called free oscillations. What we mean by free oscillations is let's not shake it harmonically, let's just ping it. We're just going to take the cantilever and just give it some initial conditions and let it go. See how it rings down. That's what we call free oscillations. We're going to do this first, and then we do forced oscillations where we actually physically drive it harmonically. There's a difference between the two. So, in this case, a simple free body diagram of the tip of the system shown on the top left is going to tell you the following. The mass times the acceleration of the tip, which is mx double dot, x is the absolute tip motion, would equal the force acting on the tip. We are neglecting gravity. We're neglecting other forces right now, so you're not interacting with the sample. So the only other forces acting on the tip are going to be the restoring force from the spring and going to be the force from the viscous dashpot. So mx double dot is the acceleration. Mass times acceleration equals the force. The force acts opposite to the motion. So you have negative kx, negative cx dot. The dots are simply dx dt's. Okay? Derivatives with time. Everyone with me? Yeah. Okay. So a simple rearrangement of that equation gets us to x double dot. So if I divide the equation through by k and move the right-hand side to the left-hand side, and I define omega 0 as the natural frequency of the oscillator, which is square root k over m, you get the equation of motion shown there, right? So omega 0 is square root k over m, and q is something called the quality factor of the cantilever, and it is given as m omega 0 divided by c, okay? So all I just had to do was divide that equation on the top by k, and then define these quantities omega 0 and q. So we've moved from having m, k, and c separately to just omega 0 and q, okay? All right. So this is a second-order differential equation. It's what's called a homogeneous differential equation. And so the solution of it is generally going to be e to the lambda t, and you're looking for characteristic lambdas that satisfy this equation. So when you plug in e to the lambda t into the second-order differential equation, the characteristic quadratic equation governing lambda is shown up there, and it's a quadratic equation. So it has two solutions, lambda 1, comma 2, and those are shown on the top. All right? And so then the general solution of the displacement x of t is going to be a linear combination of e to the lambda 1t plus e to the lambda 2t, right? So this is all, I guess, sophomore diffie-Qs and stuff. And the question is, C1 and C2 are the constants of integration, and you determine them by applying the initial conditions. So the initial conditions, you're going to supply some initial displacement at time t equal to 0, what's x? At time t equal to 0, what's the velocity, x dot? So what you do is you take this general form c1 e to the lambda t plus c2 e to the lambda t, and at x equal to 0, you equate it to x0, and take the derivative of it, x dot, and at t equal to 0, equate it to x dot 0. So from those two equations, you can get the integration constant c1 and c2. So the overall solution is shown here, and this is the solution x of t of the decaying oscillations of this oscillator, given initial displacement x0 and initial velocity x dot 0. Okay, and this is the full equation. Okay. Now, this is quite a complicated thing, but the essential idea here is that if you look at the term inside the big brackets, ultimately it is a cosine multiplied by, there's a cosine and there's another cosine. Actually, I want to check, I want to get back to you and check if one is a sine. I believe one ought to be a sine on it. So one is a cosine, one ought to be a sine, so I'll check on it, okay? But at the end of the day, something sine plus something cosine is a sine wave, right? Just phase shifted, right? You can take a sine and cosine, add them up. It's a phase shifted sine wave. So what's inside the parenthesis is basically a sine wave whose frequency is square root 1 minus 1 over 4q squared times omega 0. What's outside the parenthesis is a exponentially decaying term, e to the minus something t. So what this simply represents is an oscillator which is oscillating with a sine wave, but the amplitude is decaying with time, okay? There are two important things to keep in mind. One is that if q, this quantity q, the q factor is greater than half, in that case, we have an underdamped oscillation, okay? So if q is greater than half, then the term inside the square root is positive, and everything is okay, okay? So you get a nice, decaying signal. On the other hand, if q is less than 1/2, then the term, the square roots, become negative. Inside the square roots become negative, okay? And you need to go back to your e to the lambda 1t, e to the lambda 2t expression and rewrite them in terms of sine hyperbolics and sine and cosine hyperbolics, okay? But basically what ends up happening is that the solution becomes what's shown here if q is less than half. What you find is the solution becomes a combination of pure exponentials, okay? And what this means is if q is less than half, then if you ping it, the response is going to be as shown here. There is no oscillation. It just dies like that, right? And why this happens is basically it's called critical damping, because what ends up happening is it's when q is less than half that in this equation of motion up there, mx double dot equal to minus kx minus cx dot, at some point the idea is that the term cx dot becomes so high, so large, that the viscous force dominates the inertia, that the inertia term mx double dot is not really important anymore. At some point, you're transitioning to a simple equation where minus kx minus cx dot is equal to 0. So you don't have to worry about inertia. And that equation where you remove the inertia term is the Langevin equation. So what this represents is when you have an overdamped oscillator, you're transitioning from a inertia-dominated situation to a viscous-dominated situation. Okay? Two important points. If you look at this, in the underdamped case, if you look at how this is oscillating and decaying, the first thing you notice is that the oscillation frequency is square root 1 minus 1 over 4q squared times omega 0. That means that the oscillation frequency is not omega 0. Omega 0 is a natural frequency, square root k over m. But when you ring it and you measure the time period with which it decays, that is not going to be the same as omega 0. It's going to be different by a factor corresponding to q, depending on the q in the system. Number one. The second thing is, if you want to get a good idea of what q means, or what, to get a physical intuition of what Q should be, if you think about it, because you have e to the minus omega 0 over 2q on the outside, the whole parentheses, you can imagine that Q itself basically represents the number of cycles of oscillation for the amplitude of this ringing to decrease by, let's say, 1 over or 2 over e, let's say, to some small quantity. Okay, so you can just set the t out there to be equal to you can just set t to be equal to q basically, or t to be equal to q times the number of time periods, right? So what I'm trying to say is that Q can be thought of as the number of cycles of oscillation before the ringing motion decays by a significant amount from the initial amplitude that you give it, okay? So Q equal to 10 roughly means it's going to do 10 oscillation cycles before its amplitude decreases significantly, all right? Everyone okay with that? Okay. Any questions on this? Free oscillations before we move on. Okay? This is just, it's probably familiar to a lot of you as well. Okay. So now we're going to look at forced vibrations. And what do we mean by forced vibrations? Well, when we do dynamic AFM, we have to force it harmonically. We have to apply a forcing that's sinusoidal in time and tune the drive frequency to near the resonance frequency of the oscillator, so you can just get it to vibrate with larger amplitude. There are many ways of doing it in atomic force microscopy. The most common method is what's called mechanical, or it's also called acoustic excitation or piezo excitation. So all AFMs have under the chip holder, buried inside the system, a piezo electric shaker. It's a simple piezo that's bonded tightly. As you apply an AC signal to the piezo, it expands and contracts at the frequency at which you drive it. And that shaking transfers to the base of the cantilever, and the base of the cantilever gets shook. And so if you shake the frequency, or if you tune the frequency of shaking to that of the resonance, you're going to get this to go up and down. Okay? That's how you do acoustic mode AFM. But there are also systems that do magnetic excitation, and there are what you do with magnetic excitation is you coat the cantilever with a magnetic material, take a solenoid and apply a fluctuating harmonic magnetic field to the cantilever, and it oscillates up and down. You can also use magnetostrictive excitation. Magnetostriction is an effect by which when you apply magnetic field to a material, it stretches. This is different from magnetic excitation, which is simply magnetic forces, right? So when you apply a magnetic field to some materials, they actually undergo strain. That's called magnetostriction. So you can actually get magnetostrictive coatings, and as you apply an alternating magnetic field, the coating is going to expand and contract due to the magnetic fields, and in doing so makes the cantilever bend. Okay? People are beginning to like magnetostrictive excitation because the materials you use for magnetostrictive coatings are less prone to oxidation than materials that are used for magnetic excitation. And so when you have magnetic coated cantilevers, they tend to oxidize within 2 or 3 months unless you put them in an inert atmosphere, whereas magnetostrictive ones can last a bit longer. Photothermal excitation is a very interesting concept also for shaking a cantilever. And here what happens is you use typically a blue laser, and you provide a modulation to the laser power. So the laser falls on the cantilever, and what ends up happening is the light is converted to heat due to interactions of light with the silicon cantilever. However, if you have a coating on the cantilever, for example, you have basically a bimetallic strip. So the heating on the top is different from the heating at the bottom, and the thermal expansion coefficients are different. So the coating is going to expand more than the bottom, so it bends down. And as you modulate the laser power, this thing is then going to go up and down. Okay? So that's photothermal excitation. You also have Lorentz force excitation. This is what, for example, happens in the asylum system. And what is done there is let's say you have a triangular cantilever with 2 legs, or you could do it with a single cantilever also, but they coat a gold circuit effectively. So they put gold on each arm so that effectively you have a current carrying conducting loop effectively, right? And you just apply an alternating current to the loop and put a fixed magnet underneath it, and it oscillates. In fact, the earliest implementations of this use just the Earth's magnetic field to get an oscillation, because you have a permanent magnetic field from the Earth, and you just have an AC in a small enough, thin enough cantilever, and it begins to oscillate. But mostly they apply a fixed magnetic field as well. You can also use ultrasound excitation, which means that you have a ultrasonic generator that's sitting separately from the cantilever, and it shakes and transfers ultrasound through the air or the surrounding field, surrounding medium, whatever it is, to hit the cantilever and shake it. That's also possible. You can also do direct piezoelectric excitation. What I mean by that is, so for example, for the longest time, Vico used to sell what's called ActiveX cantilevers. These are cantilevers that the cantilevers themselves have a layer of piezoelectric material deposited over them. So what would happen is, when you apply a voltage, you're not applying it to some dither piezo that's trying to shake everything. You're applying the voltage to the coating of the piezo of the cantilever itself. So as you apply voltage, that coating expands or contracts, resonating the cantilever. Okay. So these are the different methods that are available, in commercially, basically. Okay. So I want to walk you through some important things. We're now going to look at what happens to the forced vibration response. Okay. So we did free vibrations where you just ping it and see how it decays. Now we're going to shake it. Now we're going to do 2 categories of excitation. So if we go back, I want to emphasize that there's a big difference between what I call direct and indirect excitation methods. Okay. In the top, you have the mechanical excitation. So the little wavy parts tell you that the base of the cantilever is being moved up and down. Okay. When you shake it, that's what most of you are doing. You're shaking the base of the cantilever, moving it up and down. Whereas if you do something like magnetic, photothermal, Lorentz, or direct piezoelectric excitation, or magnetostrictive, all the others that you do, the base of the cantilever is fixed, and you're physically applying a harmonic force to the cantilever. Okay? It turns out the difference between these two is pretty important. Okay? So we are going to study the force vibration response in these 2 cases. We're going to begin with the acoustically excited cantilever case. And the point mass model for this acoustic or mechanical excitation is shown here. Remember, we're now shaking the base of the cantilever up and down. That motion is y of t. All right. The absolute motion of the tip is x of t. And I need you to tell me, what do you think the photodiode measures? Does it measure y? Does it measure x? What would it measure? And why? Now, don't be shy. Just try, just guess. Measures x, right? That's what so everything I've been telling you so far would suggest it measures x, because it measures the bending angle at the end, and the bending angle is proportional to x, right? However, you have to be a little careful about this. When you move this up and down, let us say the cantilever is rigid. Let's say it does not bend as you shake it up and down, okay? And you have y and you have x, right? And they're the same because it's rigid. Y and x are going to be the same, right, if this is rigid. What would the photodiode measure? Would it measure x? No. Remember, it measures the slope at the end, bending angle at the end. If the cantilever just moves up and down like that in parallel, the photodiode does not pick up any signal. right? Because the way I think we explained this to you, right? The way the photodiode works is, it is most sensitive to rotation. Unless the cantilever bends and rotates, if it just goes up and down, it's hardly going to pick it up. Okay, because it's a triangulation. See, remember what it's doing is, it's trying to measure how the reflected spot in the photodiode moves up and down. If you do the trigonometry of this and move just the base, just the cantilever in parallel up and down, the motion of the spot here is effectively negligible. You don't see it. If this moves up and down 10 nanometers, you do the trigonometry, the distances, and you're moving up and down 10 nanometers, the distances in the laser path are microns, basically, or millimeters. You get hardly any motion in the spot. On the other hand, you rotate it, and you get a huge amplification of the rotational motion or bending of it, and causes a big motion in the spot location, okay? So that's why we say that it's a very subtle point, but I hope you've picked on it so far, is in an AFM, what we measure is the bending angle of the cantilever. And we always are trying to connect that to the tip motion. So we always make an indirect measurement of tip motion. What we measure is only the bending angle, okay? So if you think about it this way, if this cantilever is moving up and down rigidly, so that x is equal to y, what you measure cannot be x, because you would measure 0, because there's no bending angle. So what you measure is really x minus y. You measure, because if x and y are different, what you're picking up is a bending. So what you measure is x minus y, effectively. You can divide it by the length of the cantilever to get the angle, whatever, but that's just a constant quantity. Ultimately, what you're measuring is x minus y. When you do acoustic excitation or base excitation, with all 99% of you use, or will use, if you haven't used an AFM, will use acoustic excitation. That's what you're doing, okay? It's a very subtle point, and many people don't get it. But that's what you measure, all right? So, and when you do tuning curves in an AFM, all you're measuring is this relative bending between the base of the cantilever and the tip. It's a very important thing. Okay, so we're going to write our equation of motion as the following. mx double dot is the acceleration of the tip, mass times acceleration, equals the restoring force from the spring. And the restoring force from the spring is going to be negative k x minus y, so that's the relative compression of the spring, right? Minus cx dot, okay? Now, we can quibble over the damping term, because the damping term, technically with that dash spot located there, that damping term should be x dot minus y dot also, right? It should be the relative velocity also. And you can do that and you'll get a slightly different transfer function, okay? So, so keep that in mind. There are actually two different models out there for damping. If you look at a classic paper by Ansikowski, he says that the ultimate damping in acoustic excitation consists of two parts. One is a dash spot between the base of the cantilever and the tip. Another is a dash spot between the tip and some fixed reference frame, okay? So you have, keep that in mind. So this particular model, the equation at least I've written out, the damping is really a dash spot between the tip and some fixed reference, not between the base of the cantilever as shown in this picture, okay? But we can quibble about it. Don't worry about it. It doesn't matter. You'll get a slightly different answer. In fact, it's probably going to be on your homework problem, okay? So, but let's assume that it's a dash spot fixed, to a absolute reference frame. So you go ahead and write the equation of motion down, and you find the right-hand side is yt, is the base motion, and x is the absolute tip motion. But you have to remember that what we measure is not x, but we measure z, which is defined as x minus y, is the relative motion between the base and the tip. That's what we are measuring. Because if the base and the tip move the same, that means the cantilever is moving rigidly, and there's no rotation, there's no bending. And so you don't pick anything up. So what you're measuring is really x minus y. So if you write this equation in terms of z equals x minus y, you get the following equation for z double dot. Okay? z double dot plus z equals to, so z would be the observed deflection of the cantilever. Now, y, which is the base motion, is going to be harmonic. It's going to be sine omega t, right? So you're shaking it with a certain frequency and a certain amplitude, y0 sine omega t, okay? All right, so now, does anyone have any idea how much you shake the base of a cantilever by an AFM typically? Roughly? Is it microns? Is it for the dither excitation? It's usually 1 or 2 angstroms. So we're talking about shaking this up and down. Y0 is about 1 or 2 angstroms, maybe 3 angstroms. So it's very small motion typically in air we're talking about. Okay. So we're going to write now the particular solution of this differential equation, which is the steady state equation. Now, what is it going to be? The steady state solution of this is A sine omega t minus phi, okay? What I want you to remember now is that the response that you measure z happens at the frequency omega at which you excite. What I want you to note is that the response of the cantilever is not at omega 0 anymore. It's at omega. At no point have I said that omega equals omega 0. I have not said that yet. Right? So the shaking that we do need not be at the natural frequency. It can be off, it can be slightly greater, it can be slightly below. I have not said that. But the key point is that the cantilever now responds at the frequency at which you're exciting. Okay? So many people make this mistake and say, you know, it's not, no, you can choose omega to be equal to omega 0. That's your choice. But it responds at the frequency at which you're exciting it. Okay. So, a simple analysis, you can do Laplace transforms and get a solution for this equation. But what you get is this ratio A over Y0, where A is the measured amplitude, what you observed amplitude of what you measure, divided by Y0, which is the base motion, is given by this equation, where R is the ratio of the drive frequency to the natural frequency, okay? So when R equals 1, then you're choosing your drive frequency to be equal to the natural frequency. When R is greater than 1, your drive frequency is larger than natural frequency. And when you're below 1, your drive frequency is below natural frequency. And the phase of the motion, and this is actually what's plotted here is the phase lag is shown as follows, okay? All right, so this is the expression, and this expression has many important things, okay? Let us take some limits of this expression. So let's say that you're shaking at a very, very low frequency. So let's say omega is very, very low, much lower than omega 0, okay? That means that R, this ratio R, is nearly 0, okay? What do you expect? What amplitude are you going to measure if R is nearly 0? So you're just physically, if you're shaking slowly, like imagine, just slow this down. If you just take a cantilever beam, move it up and down, what amplitude would you measure using a photodiode on the cantilever? 0. Because it's not going to bend at low frequency, right? At low frequency, you just expect us to move up and down rigidly. If there's no bending, you won't get a signal. Let's see if that holds in this formula. So, not surprisingly, if you take the limit as R goes to 0 of this ratio of A over Y0, you find that the numerator goes to 0, denominator goes to 1. So the overall answer goes to 0, which means that at low frequency, you will get very small amplitude. And then as you increase the frequency, the bending that you measure starts increasing in amplitude. And of course, near resonance, when omega is near omega 0, is when it really starts shaking. And as you go, and as your drive frequency increases a lot more beyond resonance, what do you expect to happen? So let's say now that you're shaking this much faster than resonance frequency. What amplitude are you going to measure? So maybe that's not intuitive, but let's make a substitution. Let's take the limit as R goes to infinity in this. So it means your drive frequency is much higher than the natural frequency. If R goes to infinity, this ratio tends to 1, which means that when you go far above resonance, you got this situation, right? Which means the base motion equals the tip motion, okay? And that's what you pick up. And so this ratio is actually 1, which means that if you measure the amplitude above resonance, when you've gone above resonance, what you're measuring is effectively the amplitude of the shaking of the bass, okay? So you can actually get all these things, and a simple tuning curve that all of you do in AFM, if you think a little bit about it, and all this interesting information is buried in there, okay? Okay, a very, very, very important result is that if you choose R equal to 1, which is your drive frequency equals the natural frequency, if you do that, if you choose R equal to 1, you find that the, let's see, how does that work out? If R equals 1, then, correct. If R equals 1, you have 1 plus 1 over q the whole squared divided by 1 over q the whole squared. Okay, let me just think about that for a second. But the answer should be, and I'm tripping on this right now, but the answer should be that the base motion amplitude should become A over Q. Let me just take a minute and think about this. I'm not seeing this right away from this expression, which suggests to me that well, we'll come back to this and discuss this term a little later, okay? But the answer we should get is when we plug R equal to 1 in there, which is when you choose the drive frequency equal to the natural frequency, the answer should be, and I'll get back to you to confirm this, okay? The answer should be, and so I'm suspecting there might be a typo in that expression. The answer should be that the base motion amplitude is A over Q. So what this means is, it's a beautiful result. What it means is the following. It means that if you know what amplitude you're oscillating with, let's say 100 nanometers is your oscillation amplitude, you can determine what is the base motion by simply taking that oscillation amplitude and dividing by Q. So Q tells you the ratio of the oscillation amplitude you measure and the amount by which you're shaking the bass. Now, in most AFM experiments, you're driving amplitudes at 10, 20, 30, 40 nanometers. In air, the Qs are usually anywhere from 100 to 200, 300. So you can see that the base motion should be amplitude divided by Q. Okay? I'll get back to you about this. There's a term missing, I think, in that expression. I'll get back to you about it. Okay. It's okay? I think that...
Q is big. Q is big and R is 1.
Oh, so I have to include Q is large also in this. That's the key. Yeah, that's right. Sorry. Thank you. Yeah, it is right. Yeah, it is right. So then it's different, slightly different. Okay. Yeah, that's a good point. So as R equal to 1, then you guys see that the first term in the denominator vanishes. And then let's take Q being large. So in air, for example, so Q is 100 or 200 or 300. In that case, the second term in the numerator is small when Q becomes 100 or larger, okay? At R equal to 1. So for large Q and for R equal to 1, you basically have A over Y0 equaling Q. That's it. Okay, thank you. Right. So that's a very important result. And so let's go ahead and plot this for one particular typical value of a cantilever. And what's plotted along the x-axis is R, which is the ratio of drive frequency to natural frequency. What's plotted along the y-axis is this ratio of A divided by Y, which is measured amplitude divided by shaking amplitude of the piezo, for a value of Q equal to 100, okay? And this is what you get. Again, bring your attention to the following fact. At low frequencies, the measured amplitude is going to be 0 for acoustic excitation, for bass excitation. This is not true when you do magnetic excitation. It's going to switch. But for a dither piezo, you get this very interesting response where below resonance, you see the amplitude is low. Above resonance, the amplitude is higher than below resonance. So it's an asymmetric peak. You see this? So below resonance is different, above resonance is different. Above resonance, it asymptotes to a value of 1, this ratio. In other words, the bass motion is the same as the amplitude, right? Whereas what's happening when you're at 1, you're really amplifying the motion, you're really shaking it, and it responds with a large amplitude. Again, be very clear about the following fact, that wherever you choose the drive frequency to be, the cantilever always responds at the drive frequency. The cantilever does not respond at the natural frequency. However, the amplitude of the response does become large when the drive frequency equals the natural frequency, but it's always oscillating at the drive frequency. So the only indication you have whether you're at resonance or not is, so you're shaking this and it's responding at the same frequency and you're measuring the amplitude and phase of this oscillator. The only way you know if your drive frequency equals natural frequency is if the amplitude becomes very high and if the phase becomes 90 degrees, that's all, okay? So it always vibrates at the drive frequency in steady state. This is the phase response. This is, so this is phase that's negative, which means this is the phase lags. And you can show that when you're exactly at R equal to 1, the phase here corresponds to 1.5 radians or pi over 2 radians, which is 90 degrees, okay? So when you're exactly at resonance, the phase lag between drive and response is 90 degrees, okay? So two indicators are amplitude becomes very high and the phase becomes 90 degrees. These are the two indicators that your drive frequency equals natural frequency. But the cantilever always oscillates at the drive frequency, okay? Yeah?
Could you comment on the phase? Because the phase is a theoretical phase.
Yeah.
Companies that make AFMs
yeah.
don't always print out.
Oh yeah. This is okay. Yeah, this is very important. This is very important. Yeah. In most AFM systems, first of all, you will have a problem determining two things. First of all, you're not very sure if what's being plotted is phase lag or phase lead. Right? What's plotted here is absolute phase, which is why it's negative, right? But first of all, in AFM systems, you have to check to see if it's phase lag or phase lead. You need to find out, okay? How you find out is you do a tuning curve. If the phase goes like down like this, it means it's absolute phase. If it goes up across resonance, then it's phase lag that's plotted, okay? Many AFM systems actually plot phase lag. The second problem is many AFM systems don't nicely give you the y-axis in degrees with the 0 in degrees, right? It could start at some arbitrary value, change through 180 degrees, but you don't know where the 0 phase or the 90 degree phase is, and you pretty much have to look at the shape of this curve and say, okay, this is where I'm going to center my phase to 90 degrees, okay? So that's an important thing. And so the typical thing that's done is you go along the amplitude axis, go to the peak point there, and click on it and say, I'm centering my phase there. And then it just adjusts the measured phase so that that point corresponds to 90 degrees, okay? Good point. In fact, in yet older systems, even the phase you will not get in degrees, but it's in volts. And, so that becomes a problem. You have to convert it to degrees, so you got to work with the company to figure out. It really annoys me when I see phase in volts and amplitudes in volts. As I hope you've already realized that. So, okay. Thank you. Let's go to directly excited AFM cantilevers. So, this is an example of magnetic forcing, but remember it applies for magnetostrictive, photothermal, Lorentz force excitation, direct piezo excitation, all those techniques are this. In this case, the base of the cantilever is not moving, is not shaking. On the other hand, you apply the force directly in a non-contact manner and somehow to the cantilever, okay? So in this case, x is the absolute motion of the tip, and it is exactly what you measure now, because the base is not moving, okay? So in this case, everything is in a good situation. The equation of motion is not at all complicated like the previous one. You don't have to assume so many things. So mx double dot equals negative kx minus cx dot plus this magnetic force, which could be a Lorentz force also, okay? And the measured motion is x, is the absolute tip motion in this case. And let us say the response is shown as following. Xp equals a sine omega t minus phi. Again, the amplitude of response is a, and the cantilever responds at the same frequency as the drive frequency. And if you just do a Laplace transform of this equation, you can get the steady state amplitude a divided by f0 divided by k, where k is the spring constant of the cantilever, is given by this ratio, and the phase is given as follows, and r is the ratio of the drive frequency to the natural frequency. All right, so now let's look at some interesting properties of this amplitude ratio. So if you drive at very low frequencies, if you apply the force at much below resonance, r is going to be 0 nearly, right? So at small r, what is going to be the response here? What's the value? What happens when r becomes 0 or close to 0? You get 1, right? This ratio becomes 1. So in this case, when you're driving at very slow frequency, the motion is the same as f0 divided by k. In other words, you could apply a static force to the cantilever and it would bend by a certain amount, f0 by k. That is, in fact, the amount that it oscillates by. So it almost behaves like a static loading problem where you apply a force f0 and it deflects by an amount f0 divided by k, as if it's a static force. So it bends as much as if it were a static force moving it up and down. The key thing is, it's non-zero. You apply it slowly, it's going to bend slowly, right? But it bends, and you measure it. However, if you go to high frequency, way above resonance, what's going to happen? If R goes very high, you find that the amplitude approaches 0. So if you shake far above resonance, right, the amplitude is going to become smaller and smaller until it dies, basically, all right? That's what this theory would suggest. So if you were to plot this response, you get something opposite. You find that this ratio at low frequencies is actually 1, but at high frequencies it decays to 0, right? So it flips. Acoustic versus magnetic or direct excitation flips, okay? And the phase response is really classic. You know, this is the absolute phase that's plotted. It's negative, which means there's a lag. And this is the response, okay? So I hope you have come to appreciate now that, the response really depends. Simple things like the tuning curve are telling you many different things. With the tuning curve, if you do it properly, if you do acoustic excitation, you can actually measure the amount that the piezo is shaking up and down. I really encourage you to do that, because it gives you a very physical feeling because these are very small things. At the end of the day, you really don't know what's going on in the system. If you do the simple numbers, calculations with the tuning curves, you get a feel. Oh, this piezo shaker is shaking it by an angstrom or 2 angstrom. You have these numbers, that give you some confidence. If it's just in volts, you don't know what you're doing, right? So, okay, so this is important. So the way you excite it makes a difference to the tuning curve. Okay. Now, we're not going to take, so we've done free oscillations where you take the cantilever and just ping it, study how it damps. Then we studied shaking, what the steady state response is, and how it depends on the method of excitation. Now we're going to shake it near resonance and bring it close to a sample so it interacts with the sample, okay? That's what we're going to do. And I will start this part, and we'll probably finish it in the next lecture. But I take, in particular, the example of magnetic excitation here, for which the equation of motion was shown to you already. X is the upwards deflection of the tip from the equilibrium, from the non-deflected position. D, the small d, is the tip sample gap, just like what we have studied before. It's the same d as we've had before, except now d can be a function of time because it's oscillating. So the tip sample gap can change with time, or the indentation can change with time. It's a dynamic situation. It becomes a function of time now. Okay? So the equation of motion that's shown is the same as in the previous slide, but now we have to account for the tip sample interaction force, since there's an additional force between the tip and the sample. That force, FTS, is going to depend on the gap. The gap D is Z plus X, okay? From the little geometry that I've shown out there. So the equation of motion becomes what is shown here, and the key thing I want to point out to you is F as a function of D, FTS as a function of D is nonlinear, correct? Like if you have van der Waals forces, you have 1 over d squared dependence, right? Or if you have electrostatic forces, it's 1 over something, right? And if you have repulsive forces, it turns around. The force interaction turns around. So the key point is that suddenly that term FTS makes that entire equation nonlinear, right? Because FTS is a nonlinear function of d. D is z plus xt. This is a diffie-q in x. So if there's a term which is nonlinear in D, that term also makes it nonlinear in X. And so the diffie-q becomes nonlinear in X. Okay? So we have a nonlinear differential equation now. So we can't just use Laplace transforms to look at what happens to, the response. Okay? So we therefore have to make life a little simpler and try to do a linearized analysis of the problem. And this is what the linearized analysis is going to do. This is our equation of motion from the previous slide. And we're going to study this problem in 2 different ways. Let's say you're at a certain z, right, and there's some interaction forces between the tip and the sample. Well, what's going to happen is, if there are attractive van der Waals forces, the cantilever is going to bend slightly, right? This is what we did when we did FZ to FD conversions, that at a certain z, there's a little bending of the cantilever, right? So as it bends, let x star be the new position of the tip after it bends, okay? And so x star is the equilibrium position of the tip, and at equilibrium, remember that x double dot and x dot are going to be 0. It's under static equilibrium conditions, no inertia, no time-dependent terms. And let's remove the forcing from it. So equilibrium is simply given by x star equals 1 over k FTS. Okay? So what it means is, under equilibrium conditions, the attractive force due to interactions equals the restoring force from the cantilever, right? There's going to be a balance between the two, and the x location at which they balance out is x star. That's it. Okay? Now, so what we have is the surface is here, the cantilever is slightly bent. Now we're going to oscillate it a little bit about that equilibrium position. So we now say that x of t is going to be equal to that equilibrium position x star plus x bar t. X bar is the perturbation, time-dependent perturbation about that equilibrium position. Okay? We substitute equation 3 back into equation 1. And the first thing you would notice is that x star, two dots of x star, which is 2 time derivatives of x star, go to 0 because x star is equilibrium. It's not dependent on time, right? It goes to 0. So all the x star dot terms go to 0. And you end up with an equation shown in equation 5. And you can simplify life a little more also by looking at the right-hand side. You remember the right-hand side has FTS, right? Now, FTS is a function of D. D is Z plus X, but X is now this equilibrium X star plus the perturbation on it. So FTS is FTS of Z plus X star plus this time-dependent perturbation. Now, we're going to do what's called a linearized analysis. So we'll now assume that X bar the perturbation is really, really, really small. So we can replace the expression for FTS by Taylor series approximation. Okay? So remember, if something is a function of x bar, and x bar is very small, Taylor series is simply going to be the quantity at x bar equal to 0 plus the linear term proportional to x bar plus a quadratic term x bar squared and so on. We just do the linear term, and the linear term is going to be this derivative FTS with respect to the gap D evaluated at the equilibrium position D star times x bar. Okay? So it'll become, just try to, basically all I'm doing is I'm replacing the FTS term by its mean value and by its slope. So I'm just saying that, look, it's a nonlinear function, but locally let's call it simply a number plus a slope. So locally I'm just doing a linear approximation of it as a straight line. That's what I've done basically. Okay? So what I've found is we come to equation 7, and the equation 7 is really, really interesting. It says that the simplest understanding of what the presence of tip-sample interaction force does to everything we have studied so far, in terms of tuning curves and stuff, is shown down here in equation 7. So on the right-hand side is a forcing term. That hasn't changed, so you're still shaking it the same way. The effect of the tip-sample interaction force, the most important effect, is inside this parentheses. What you find is that it introduces an additional, or it changes the effective spring constant of the cantilever. Because if you think about it, the term that's inside parentheses here is basically the restoring force of the cantilever, right? It would be Kx typically. Now it is, if I multiply this whole equation by K, what's inside the parentheses is really K minus the gradient of the tip-sample interaction force. So in this linearized analysis, or what we call a lowest order analysis of the problem, the effect of the tip-sample interaction force is to change or shift the stiffness or the natural frequency of the oscillator. So in other words, what happens is, if this gradient is actually a positive gradient, then what you have done is you made this entire term reduces below 1, and so the frequency becomes less. On the other hand, if you have a repulsive gradient, which is negative, you actually increase the frequency and increase the stiffness, okay? So this is interesting. What ends up happening is, the effect of the tip-sample interaction comes up in a shift of frequency, or a shift of effective stiffness of the cantilever. That gives you some ideas on how do you want to detect this, because ultimately we do AFM to detect these interaction forces, right? I mean, this cantilever tuning far away from the sample is exciting for nobody except mechanical engineers who design cars, or something like that. So it's the interaction properties where the action is. Okay? So what we have effectively done here is the following. As I mentioned to you, the tip-sample interaction force, FTS, as a function of D, is shown in red here. We did this entire analysis about an equilibrium gap D star. There's an equilibrium gap D star. So at a certain Z, you get a certain cantilever bends, and it reaches an equilibrium position, an equilibrium gap D star. What we have done is we have replaced the full nonlinear interaction potential by a straight line, which is the gradient of the interaction force, FTS, partial FTS, partial D, evaluated at that point. That's what we have done. That gradient is what appears in the equation of motion shown on the top left. And if you sort of multiply it throughout by omega squared, what you find is that the presence of the gradient, what it's done is it shifted the natural frequency of the oscillator from omega 0 to omega hat, where omega hat is related to omega 0 by that expression, which is 1 over 1 over k, partial FTS, partial D. All right? So this is the most important result, that the simplest understanding of what the interaction force does is it shifts the effective natural frequency of the cantilever. And it shifts it by an amount that's related to the gradient of the tip-sample interaction force. So if you have a way of measuring frequency shift, you're effectively measuring gradients, tip-sample interaction force gradients. So Already this is slightly different from FZ, FD. In FZ, FD, you measure force directly. As soon as you go to dynamic AFM, suddenly we're talking of measuring gradients of force. That's a very important difference, okay? So when you have an attractive force, then this gradient, so attractive force would be, you know, when the curve goes down, right? So if you have an attractive force, you know, Van der Waals force, 1 over d squared, it goes down. In that case, partial F, partial d is going to be positive, correct? Like as shown there, you see the dotted red line, right? That dotted red line has a positive slope, right? So that's an attractive gradient region. And so if you have an attractive gradient, partial F, partial d is going to be greater than 0. If that's greater than 0, the effective natural frequency goes down below omega 0. So in the presence of an attractive force, the natural frequency of the cantilever slows down, okay? On the other hand, if you have a repulsive gradient, so in other words, if I were on further to the left of this curve, partial F, partial d would be a negative gradient, in which case you would get an increase in natural frequency. So this suggests that if you were just monitoring how the natural frequency of the cantilever would change, as you come closer to the sample, first it would go down because you have negative attractive gradients, but when you come closer, it starts going back up because you have positive gradients after that, okay? So the shift in frequency effectively is going to be telling you something about, and so this idea is actually going to be used later in frequency modulated AFM that Professor Reifenberger is going to talk about later in the class. Okay, so I want to just conclude with a very big caveat. This understanding is great, this zeroth order understanding of dynamic AFM with the tip sample interaction force is very simple, but what the question is, what is the assumption inside it? And ultimately the assumption is this, right? So let's say you're located at some equilibrium position shown by the green dot. So this is a tip sample interaction curve. You've separated the cantilever and the tip, and under the static force, the cantilever bends a little, and you have an equilibrium tip sample separation of d star, okay? And you're oscillating, you're driving the cantilever, oscillating with an amplitude A about that equilibrium position. How large should the oscillation amplitude be in order for this simplified analysis to hold? So we did a linearization, right? We replaced this interaction force by a linear straight curve, right? Now, and that's the first term of the Taylor series, right? So the question is, for what amplitudes can I approximate the interaction force by the straight line, the straight dashed line? You can see the straight dashed line does not obviously represent the curved FD curve, but that's the assumption. So how big should the amplitude be, or how small should it be in order for this to apply? Any ideas? So does anyone have a feeling for, if this is a DMT interaction, does anyone have a feeling for how far Van der Waals forces exist in gap? So if the tip and the sample are separated by 100 nanometers, do you expect to see Van der Waals forces at 100 nanometers? I mean, these expressions you've done in the earlier class. You pretty much, Van der Waals, you're talking about 1 or 2 nanometers, 3 nanometers gaps, okay? So in other words, you have to get a physical feeling that this entire potential well we're looking at in air between the tip and the sample, the width in terms of d is maybe 3 nanometers. And at 3 nanometers, the interaction force is so convoluted going through a negative positive, right? So how big does the oscillation amplitude have to be in order for us to be able to say that locally it's a straight line? It has to be really, really small. Really, really small, right? If this whole range is really 2 or 3 nanometers, that guy probably has to be 1/50th, maybe a fraction of an angstrom, or maybe an angstrom, at least, at most, for this linear approximation to be valid, okay? So this is great, but what I'm trying to say is none of you, unless you spend 5 more years in AFM, are going to anywhere approach the point of 1 angstrom AFM oscillation amplitude. This is what the really high resolution AFM people do. So sub 1 angstrom oscillation amplitudes are really hard to come by, and there's a race amongst AFM scientists to try and get, I got half a nanometer, or a 1 angstrom oscillation amplitude or less, So the point is, this is great, but in reality, this is not what you see. Most of you are not going to see that. What most of you are going to see is the following situation. I just want to end with this, just going to highlight to you. This is a tuning curve that's taken on a HOPG substrate of the cantilever. So you sweep the drive frequency up, sweep the drive frequency down. When you're far from a sample, you follow the solid black curve. You see the solid black curve? Right? There's a backbone solid black curve. And that curve is interesting because on the left-hand side, amplitude is low. On the right-hand side, amplitude is larger. So can someone tell me, is this acoustically excited or magnetically excited cantilever? Just by looking at this. Don't look at the red and blue curve right now. Just look at the black background. It's acoustic. Because on the left side, the amplitude is low. On the right hand, the amplitude is higher. Just by looking at it, you can tell this is acoustic excitation, right? Of course, there are, it's not perfect like theory. There are other things that happen. But the phase, this is the phase, just like I showed you, goes through 0 and goes through minus pi, or minus 180 degrees. However, that's the black. However, the reds and the blues tell you what happens when you come close enough to the sample and you sweep. So as it oscillates in amplitude, now, what's going to happen is when you're below resonance, it's oscillating small. As you increase, the amplitude picks up and it starts tapping on the sample. And as you go above resonance, the amplitude becomes small again. But the resonance curve changes dramatically now. What happens is, as you sweep the frequency up, the amplitude follows that scheme. It goes like that. As you sweep the frequency down, it does this. Right? This is not the simple frequency shift that we talked about. It's very complicated behavior. There are jumps happening, all kinds of. The phase behaves in an interesting manner. It jumps up and down. So my point is that in reality, when you do experiments, the effect of the tip-sample interaction force is much more than the simple change in resonance frequency that we talked about. Okay? So we'll study more about this in the next class. Thank you very much.